my great pleasure to get to introduce our next seminar speaker. Professor Greg Parsons is coming to us from North Carolina State University, where he's a professor in chemical and
You can read it on the sign right there.
biomolecular,
Yeah.
engineering at North Carolina State University. I get to work closely with Dr. Parsons in one of our research centers, and it's been a great pleasure. And this is through the Semiconductor Research Corporation, which he's had a lot of activity in, and the SRC recently awarded him the Aristotle Award for outstanding contributions to the semiconductor industry for this year, 2025. And so numerous other awards that he's received, and is a named professor related to cellulose acetate, I think, at North Carolina State University. So today he's going to be talking about atomic scale processing and the Ångstrom era. So I'll turn it over to you, and thank you so much for being here.
All right. Thank you, Welton. Thank you. You all hear me okay? You guys are in the back row, so I'm gonna like give my lecture from way up here. It's okay with you. So I appreciate having you and being invited to come out here and supporting my travel and letting me visit you guys. I enjoyed my lunch with the grad students today, learning a lot about what's going on here. But I'm going to tell you about some of the work we're doing at NC State, and you can see the title. I'll tell you a little bit about the title. So we do work in semiconductors, and so we are thinking about transistors, because transistors are everywhere in semiconductors. They're the key building block of every electronic device you have. In 2007, Intel came out with this transistor that was really important at the time because of that white thing right there, those white letters right there. It says high K. So this was a hafnium oxide thin film that took the place of SiO2. And I was talking to somebody at lunch today. This is one of those things that, well, before 2007, I've been in this field for a long time. And in the 1990s, people said, you know, at some point, people are going to have to get rid of SiO2 and replace it with something. But there's a physical problem. It's never going to happen. It can't happen because SiO2 has very special properties, and once you replace it with something else, it's not going to work as well, and the devices just won't be able to work. And so a lot of people thought it would just never happen. And then Intel did it, and now everybody in this room has hafnium oxide transistors in their pockets. So things that we think are impossible are not impossible. So I'm going to show you some things that you're going to say, there's no way that we can do that in the future, but it's going to happen. And it's if you think about it, it's pretty amazing. So in any way, the point here was that this transistor was 45 nanometers across. And we called that, in 2007, we called that the 45 nanometer node, because the devices were 45 nanometers. That makes sense, right? So if you count the size of a silicon atom, that width from where is it? From here to here, the number of, and here, this is the silicon right here. So the electrons travel from here to here in the silicon. That's only 175 atoms. So that's how many atoms are in that transistor. And I'm going to show you that we're going to make, now the transistors are much smaller, and the number of atoms, of course, is also smaller. So this is, in 2020, a transistor that was shown by IMEC, which is in Belgium. And what they showed is they showed a transistor that uses something like this. This is a two-dimensional metal chalcogenide, and this is tungsten diselenide or tungsten disulfide. And you can see that this two-dimensional material is only 3 atoms thick. And the width here is 18 nanometers, which is 105 atoms. So this layer, you can actually count 300 atoms per square centimeter, is all it's needed to make that device. Well, this device was demonstrated in 2020, and it's 18 nanometers. So what node do you think that is? Remember, the 45 nanometer transistor was the 45 nanometer node. So this is an 18 nanometer. So what node is that? Correct. It's not the 18 nanometer node, okay? And it's not the it's not the point. Anyway, the names don't mean much of anything, okay? I'll show you that in a minute. But what's going to happen is, so this device right here, you can see it's pretty simple. But actually what has to happen is, to make these things functional, you have to build them into transistors that look like this. And this is called a complementary field effect transistor. And this is what's being projected in the future now. And you can see that these layers, these little yellow layers, those are two-dimensional channels where the electrons will flow. And it's called a CFET. So here I'm going back. This is Intel published this in 2022, their roadmap. So here is their roadmap. This was where they were in 2007, the 45 nanometer node. And then they went like this. They went to the 32, 22, 14 nanometer, 10 nanometer. Then they went to the 7. Is that a typo? They left off nanometer. They decided to drop the nanometer because because the 7 is not a 7 nanometer anything. It's just a 7 node, okay? Because these nodes don't really associate with size. And then they went to the 4, then the 3. So this is about where we are right now. So what's happening next is now they put back a letter. Now it's 20A, and that is the Ångstrom era. Okay, so we are entering the Ångstrom era, where now, because the devices are getting small, now they want to publicize, hey, we are really working with devices that are at the Ångstrom scale. We can't even talk about nanometers anymore. And these devices are becoming to the point where the number of atoms is less than 100 or even less than tens of atoms that are needed to make these devices. So this is Intel's roadmap. This was in 2022. And oh, by the way, there's that CFET. It's down in here. They're predicting it for the 18A node. Here's IMEC. I told you about IMEC. They published a roadmap, and they have an Ångstrom era. They said they call the N7, N5. They didn't call it nanometers. They just call it N. But everybody knows that's supposed to be nanometers. But it's anyway. So now they have the A. Okay. So this is where we are right here. This is 2024, 2026. So we're right at the edge of the N to the A. So we are entering the Ångstrom era. And down here, you see that? There's the CFET. That's that device that people are talking about in the future. Here is the IEDM or IRDS roadmap, 2022. And they call it the 1.0 nanometer equivalent. They even use quotes, because they know that they're saying it's not really real what it is, but that's what they call it. And so they're calling it, it's also the Ångstrom era. So anyway, that's where we are. And there's the CFET. Okay. And this kind of transition is also occurring not just in logic, but also in memory devices. Up the road, I was at Micron today. They're doing some really amazing things, and they showed me some devices that are even smaller than what I was just showing you here. So they are making structures at high manufacturing that are less than 10 nanometers in dimension. The other thing that's happening is we are using more and more energy for doing computation. So I think about this like 50 years ago in the 1970s, how many of your parents had a computer in the 1970s? Nobody had a computer, right? So how much energy did we use, did the United States or the country use to do computation 50 years ago? Basically none, right? We didn't use hardly any energy to do computation. How much energy do we use to do computation now? We use a ton of energy. You guys in the back row are looking at your laptops, which is fine. I got no problem with that. But you're using energy right now in doing computation, and everybody around the world is doing this, and we are using a lot of energy. And if we keep increasing the amount of, oh, by the way, does anybody use AI? You guys ever use any of that? Can you avoid it? Can anybody not? Has anybody not used it? You don't even know. My wife says, I don't like to use AI. And I tell her, well, you're doing it. You just don't know it. Everyone's using it, right? And it's using data centers. And oh, by the way, I just heard on the radio this morning, I listen to, when I travel, I can listen to radio from North Carolina because it's over the internet. So I was listening, there's a controversy that somebody's going to build a data center in North Carolina and people are concerned about it using too much energy. Where are we going to get the energy? So we need new devices that consume less energy. So that's really what we need. We don't need less devices. What we need is we need new devices that consume less energy. And these angstrom scale devices, the way we design them, they have the capability or the promise of using much less energy than the current devices we have now. So that's where we are. So this is actually where I'm from. This is NC State University. This thing right here is our library. Over here is my building. That's my building right there. This is what we call our Centennial Campus, which is a new part of campus. It's very close to downtown. There's downtown Raleigh. It's the capital city. It's kind of like Boise in some ways. It's capital city. We're in the middle of the state. We got a big state university. There we are in Raleigh. If you go to the mountains in the west, go to the beach in the east, and there's our campus right there, right in the middle. And there's my lab, which is right there too. And we are in the Research Triangle Park. And so we have some other, there's our university right there in the lower right, NC State. And right next to us, we have some other universities, UNC Chapel Hill and Duke University. And anyway, you might have heard of those. And don't confuse UNC with NC State. Those are two different schools, two different football coaches. Everything's different, okay? So don't get that confused. We're red, they're blue, okay? All right. Also, my department's 100 years old this year. The faculty are not 100 years old. The department is 100 years old. Actually, some of the faculty are getting up there, me included. But in any case, we have a lot going for us. We have 150 PhD students, and we have getting close to 40 faculty. So you do the math. Each PhD student stays here for about 5 years. So you divide that by 5, and what is that? 3 times 30? 30 times 5 is 150, is that right? So that means we're graduating about 25 to 30 PhDs every year. So that's a large number of PhDs that we're producing in our department only. And that's just one part of the College of Engineering and one part of the university. So we have a lot of research going on at NC State. So I do a lot of different things, and I won't go through these, but you can see we're getting support from Semiconductor Research Corporation. We have a collaboration with IMEC. We're also working on some kind of interesting materials, for example, for 3M. We also have, this is supposed to say photoelectrochemical. We have a project with the Department of Energy looking at CO2 reduction for creating solar fuels. So we want to use sunlight to turn CO2 into methanol, which you can burn to make CO2. So anyway, we have a large number of things going on. But really what I want to tell you about is, oh, something happened with this slide. That's okay. What I want to tell you about is I want to show you the process by which we make, or not we, but in general, how one would make a structure like this. So what you see is you see a wafer with 2 patterned films on it. You got this orange film, and this is supposed to be green, but somehow it didn't show up as green. This gray thing on top. You can see there's 2 films on two different patterns, one on top of the other. How do you make that? Well, first thing we got to do is you deposit a film, and then you deposit a photoresist. You probably already know this. And then you use a mask and you shine light, and the light then transforms the photoresist. Then you remove the photoresist, and then you do an etch step, and then you strip off the photoresist, and that's your first step. So now you've patterned one material. Now you want to do the other material. And what you do is you do a second photoresist, okay. I'm going to show you this a little bit differently. So this is the light. I didn't put in here the photoresist, but this is the light shining down, and this is where I want to put my film, and it's perfectly aligned. See those yellow? That's the light coming down. The light is perfectly on register with the metal, with a line underneath. And if I do that, then boom, I can deposit that metal exactly where I want it. But remember I showed you these devices are like 10 nanometers. So that means, and this is 300 millimeters across. And so if that light is off by a little bit, it's going to cause a problem. So that's misaligned. You see that? The light is not exactly aligned with the other one. So when I deposit, it's going to be shifted. And that means that line that might connect, it's supposed to be right on top, but this one shows it's a little bit off, and it could lead to a short or a defect. And this is the biggest problem. This is what's called self-alignment, okay? edge placement error. So this edge is not where it's supposed to be. It's a little bit displaced. And so this needs to be aligned with atomic scale angstrom precision. That's why we're in the Ångstrom era. So how do you do that across a 300 millimeter wafer? One way to do it is you deposit something. I'm going to call it area-selective deposition. I'm going to deposit something on the bottom, and then I'm going to do a misaligned structure. And now it doesn't short because I was able to do this selective deposition. I was able to chemically pattern a film. So you notice that? So this is, how do I do this? It's like, I'm going to create a pattern film using chemistry. I'm going to only form the film where I want it. And that allows us to have a little bit of misalignment and still survive. Okay, so how do you do this? What we do is, ideally, you would have some chemistry going on, and it would react in some places and not in others. Well, that's nice, but in fact, it doesn't really happen that way. What we end up with is we end up with a film where we want it, and usually some junk. And this junk can cause a problem. So we have to avoid that stuff. And this is important for many applications. I showed you already this, what's called fully self-aligned via. That's this device I just showed you, but this is a more accurate representation of what it looks like. But there's many applications for this, and people are interested. This is what I talked about over at Micron. They're very interested in this chemistry, and I showed them what we're working on in this chemistry. They're working on this too. And what I told them about this. This is something that people have been working on since the 1960s. People discovered in the 1960s that you could take silicon and you could do a selective deposition of silicon on silicon without a reaction on silicon oxide. And the reason it works is because there's a chemical reaction where on one surface, the chemistry is thermodynamically favored for deposition, whereas on the SiO2, you can get a little bit of deposition, but what happens is when the reactant, in this case silicon tetrachloride, comes in, it can do something called disproportionation, and it makes two of these things, SiCl2, and that's volatile. So the thermodynamics says it wants to make this SiCl2, whereas over here it wants to make HCl. So we have deposition and etching occurring at the same time, where one occurs in one location and one occurs in another. And that's why you can't see it very well here, but you can get near perfect selectivity for this process. And this process is used in high volume manufacturing. And if you have a cell phone, your cell phone was made using this process. So you have this material patterned like this in your pocket right now. The problem is that this kind of temperature requires 700 degrees. And it only works for selective epitaxy. So we're inspired by this. Can we do something like this at lower temperature? And can we do it with a wider set of materials? So this is the challenge that we took on when I started doing these projects. So what we do is we use a process called atomic layer deposition. And maybe I think some of you probably know about it. What happens is you have a surface that has a reactive element on it, and you bring in a reactant that reacts with that surface, and that material then partially decomposes. In this case, I'm showing a molecule that's trimethyl aluminum. It reacts with water on the surface, and then that reaction saturates. It consumes all of the available sites. And then when it does, what we can do is we can bring in a second reactant, and then that reacts again, and that does a saturation also, and we can go around and around this cycle and build up a film layer by layer. So that's an ALD cycle. People show these cartoons quite a bit, but I like to point out that these cartoons can be misleading. For example, the saturation does not always produce a full monolayer. So people say it's one monolayer, but it's not always a full monolayer of material. And there's other problems too. The other thing is that this cycle depends on what your starting surface is. If your starting surface does not have reactive sites, then you have to create those reactive sites before it can start to grow. So that's one of the things that we're interested in. We do all of our work in homemade reactors because they're inexpensive and we can fix them when they break. And this shows an example of the thickness as a function of cycle. We're building it up one layer at a time, and so the thickness increases linearly with the number of cycles. The other thing we do is we can do some sort of in situ characterization. This is a quartz crystal microbalance that measures the mass. And what we see is when we measure the mass, you can see these steps. These steps correspond to each cycle in the process. So the mass increases stepwise. This is aluminum oxide and this is zinc oxide. And look at that. It grows much faster for zinc oxide than aluminum oxide. So why is that? Anybody want to tell me? Why is there a larger mass increase for zinc oxide compared to aluminum oxide? Anybody know anything about the periodic table? Where is aluminum in the periodic table and where is zinc? What? What do you got? What do you think? What's that? I can't hear you, but okay, I can't understand what you're saying, but I think you're saying that zinc is heavier than aluminum, right? Molecular weight is larger. So when it lands on a surface, it adds more mass. So that makes sense. That's only half the answer. That's half the answer. That's correct, but that's only half the answer. The other reason is that aluminum is trivalent. So it has 3 ligands on it. Zinc is bivalent. It has 2 ligands on it. So when one ligand reacts on the zinc, it leaves 1 ligand behind. When trimethyl aluminum reacts with 1 ligand, it leaves 2 ligands behind. And those 2 ligands that are left behind block more of the deposition than the 1 ligand on the zinc oxide. And that's why you get a higher mass. It's because of the chemistry associated with the reaction and the weight. So those 2 factors. So you can learn a lot about the ALD process from this kind of data. Okay, so moving on, there's a picture of our reactor. If you want to make one, we can help you make one. So this shows, again, the sequential reactions. And what I'm going to show you is what happens when you do this process on 2 separate surfaces. The starting surfaces are different. And how does that lead to a difference in the growth? So what I'm going to do is I'm going to start on a surface that has a lot of reactive sites on it. And when I start to do this process, this is titanium oxide using titanium tetrachloride and water. What happens is that we see linear, very linear growth immediately from the beginning. So that means that those reactive sites, the first cycle, the first step, it starts to grow right away and just continues to grow. If we do the same thing, now I'm going to take a surface and I'm going to remove the oxide. So all I have is silicon on the surface. The titanium tetrachloride doesn't really react with the silicon. And actually, the water doesn't really react quickly with the silicon either. So this surface is kind of inert. But if I keep exposing it, eventually it's going to react. So what I see is some sort of delay. I see a delay and then, oh, okay, whoop, up it goes. And these lines this line is a fit to an analytical model for how we would expect a nucleation to proceed. So what you can see here is that I expect that on one surface I'm going to get 2 nanometers, and on the other surface I'm going to have hardly any. So that means I can get about 2 nanometers of selective deposition. Well, fine. How many nanometers do you need? If you need 3 nanometers, this ain't going to work. And most processes you need 3, 4, 5 or more. So we need some other way to get this process to be better. So we want to know what thickness is possible. So that's kind of what we're working on. So here's some other information. So this is ellipsometry data. This is data collected using an in situ ellipsometer. And you can see it looks very similar to the ex situ ellipsometer data. So here's a nice experiment that we did. What we did is we took a pattern that had SiO2 and silicon lines on it, and we made this. This surface has got hydroxyl groups, which are reactive, and the silicon does not, so it's non-reactive. It's non-reactive, or kind of not very reactive, but partially reactive. When we do a metal oxide, and if we do enough metal oxide, we see growth everywhere. So this is what we call a non-selective process. Okay, so that means the metal oxides, there's no reaction contrast or limited reaction contrast. We want to add some contrast. We want there to be contrast. So we hypothesized that there would be contrast if we did a different process. And this process we're going to do is we're going to do molybdenum deposition. Molybdenum is a very interesting material. It's high conductivity, and people are looking at it as a replacement for copper in some of the advanced devices. So we're interested in how to deposit it. It turns out that in this case, there is chemical contrast. So the molybdenum will react with the silicon, but the molybdenum does not tend to react with the SiO2. So that's great. We're able to make a selective deposition. And if you look at cross sections, you can see some very nice. This is about 12 nanometers. Remember the one I showed you before was 2 nanometers. So this is pretty good. That's a factor of 6 better than what I just showed you before. So this is a pretty good improvement. So we like that. That's really great. But then what we wanted to do was we wanted to think about how might we put 2 selective deposition processes together. If you really want to think about building a device from the bottom up, selective deposition, put some material there, put some material there, you need to do multiple area selective deposition processes back to back. So that's what we were trying to do. We were trying to say, could we do area selective deposition back to back? So we said, okay, let's do this. Let's put down this molybdenum, and then let's try the metal oxide. Maybe now the metal oxide, maybe it won't go on the molybdenum, and we can grow it, because over here, see that, it grows on both the silicon and silicon dioxide. So maybe it won't grow on the molybdenum, it'll just grow on the silicon dioxide. Well, what we found was the opposite. It grew on the molybdenum, but not on the silicon dioxide. But wait a minute, over here, it grew on the silicon dioxide. We did this process, and we changed this surface, but then this surface, it doesn't grow anymore. And it's not just a little bit, it's quite a bit. It's quite a bit. So what we think is happening is that on this surface, this SiO2, we have a lot of different reactive groups. And when we bring in this molyhexafluoride, we think that it's stripping off these OHs and turning them into SiF groups. And we also think there's these what we call siloxane bridges. We think that those are not being stripped off. So what that means is that when we do this deposition, when we do zinc oxide, this is on without the fluorine, this is with the fluorine. Notice that? Now we're getting about 8 nanometers of selective deposition. Over here, this is TiO2, we're getting about 6 nanometers. Aluminum oxide, it doesn't notice that the fluorine is on the SiO2. The fluorine makes a big difference for the zinc oxide and titanium, no difference whatsoever for the aluminum oxide. What's going on there? So what we think is happening is that these reactants, the diethyl zinc, they do not react with the fluorine, and when we bring in water, that also doesn't react, so we're able to get selectivity. However, when we bring in the aluminum, it tends to, remember those bridges I told you about? See that bridge? It's reacting with that bridge site. That's what we think is going on. And therefore, that's why we get no selectivity and good selectivity for these other materials. So I just showed you that we're able to get this, and this is some pictures. So this is a cross section. What we have here is this is the silicon, and on top of the silicon is the molybdenum, and on top of the molybdenum is the zinc oxide, and there's no zinc oxide over here. And this is the titanium oxide on top of the molybdenum, and none over here. And this is another picture. Oh, and here's the aluminum. Aluminum is everywhere. So you can see that we have been able to do this selective deposition bottom up from with this kind of careful passivation. Can we do this on something else? The other thing we're interested in is silicon oxide and silicon nitride. can we get selected? There's very many cases where silicon oxide and silicon nitride are present when we make devices, but those two materials are very similar. As a matter of fact, if you take silicon nitride and you leave it in air, you know what happens? What do you think happens to silicon nitride when you leave it in air? I'll give you a hint. It changes into something else. What's that? Come on, Elton. It's exposed to oxygen and water vapor. It oxidizes. Silicon nitride turns into silicon dioxide, okay? So if you have silicon nitride next to silicon dioxide and you leave it sit in the air, what you have is you have silicon oxide everywhere, okay? So somehow you have to clean the surface and then don't let it oxidize. You got to keep it away from oxygen, and then maybe you can get some reaction or one that occurs on one and not the other. And we were wondering about this fluorination. Maybe this fluorination would work. Maybe it would fluorinate the oxide, and maybe it wouldn't fluorinate the nitride. So this is a starting pattern we started with, and this is some AFM images. These were collected in your building downstairs. This is a collaboration we did with Elton and was just published. So this is the starting surface. You can see the pattern on a SEM and also the IR and AFM. And it turns out it works. So what happens is we are able to deposit on the silicon nitride and not get no deposition on the silicon oxide. So that fluorination step, it fluorinated the oxide, and so it couldn't react. And so it didn't fluorinate the nitride, right? Obviously, it didn't fluorinate because it reacts. Is that true or false? Actually, the fluorination step, it actually fluorinated the nitride more than it fluorinated the oxide. If you look at how much fluorine is on the surface, the nitride surface, where we see a ton of deposition, it got more fluorine than the oxide. But somehow the fluorine on the oxide turns off the deposition, but the fluorine on the nitride does not. We don't understand that. It is what it is, but we'll take it. It works. Okay? So this is of interest. I just showed this at Micron today, and they're like, oh, this is really cool. And actually, did you see the Tokyo Electron talk at the ALD conference? Tokyo Electron showed a similar result. And it was based on some of the results that we got from our lab, how the fluorination helps passivate the oxide. What's that? We can talk, I'll show you the data later. They show, Tokyo Electron is a company that makes machines, and they're trying to sell machines to do this, and they showed some results that's much better than what we can do. They took the process and figured out how to make it better. Anyway, and this shows the AFM IR results, so we can see some of the defects here on that, using that tool. So this is, I don't know if you're going to be able to see it. This is a top-down view of those surfaces after deposition. This is before and after. And you can see these light gray lines after, they're still light gray, and the dark are still dark. That means you're not getting any deposition on there. Now, if I zoom in a little bit from where I'm standing, I don't know, maybe you can, I'm going to come back here and see if you can see it from back here. Yeah, you can see some dots. See those dots? There's a dot there, a dot there, a dot there. These are defects. These are failures. See those failures? So what we have to do is we have to go in and count them. So I asked my student, I said, draw a red circle around every dot that you can see. So boom, those are all the red circles around every dot. It's a little bit hard to see, but there's a lot of red dots. And I said, I want you to calculate, I want you to go in and figure out what fraction of this surface is covered by those dots, by the defects, those little tiny dots. It turns out this, where we want the film, it's 100% covered, obviously. It's covered everywhere. Where we don't want the film, it's 3% of the surface. So what we do is there's a calculation you can do. Here's the calculation, I think. Yeah. So it's 3.8%. So this is the fraction coverage on the growth surface. That's 1. That's the fraction on the non-growth surface, 3.8%. So you do this little math here and you get 92.6. 90, that's the selectivity, 92.6% selective. And that thickness is 10 nanometers. And I showed this to one of my industry, I showed you on my first slide, oh yeah, we get funding from industry. I showed this to my industry people, the people who fund this work. And it's like, this is like a world record. No one's showing anything like this. This is really good. And the industry goes, that's terrible. We need it much, much better than that. So if you want to do this in manufacturing, 93, that's horrible. It needs to be 100. 100, no one gets 100. Well, that's what we need. We need 100. Okay, we'll get 100. So we're working on how do we get 100? And it needs to be, oh, by the way, 9 nanometers? No, it needs to be thicker. This is really hard, but that's what we're doing. And you know what? Some people would say, that's impossible. Remember what I told you before about what people thought was impossible? It's going to happen. Someone's going to figure it out. Why not us? Okay? Why not you guys in the room? We're working on this. Why can't we? Someone's going to figure it out. Okay? It seems impossible, but it's going to happen. Remember this picture I told you? I said this inspired us. We want to do deposition and etching. So I asked myself this question after I already knew the answer. So it was a bit of a cheat. So I asked myself, what if I have two materials present? Okay, when we do area selective deposition, we have two surfaces present. So I'm going to start with a surface that has two materials present. Is it possible to find one set of reactants that will react on one surface to cause deposition, but that same set of reactants on the other surface will cause etching? So what I need is the correct match of two starting materials and combined with the correct selection of two different reactants. So it's a combination of 4 different things that has to work together. And oh, by the way, has to be the right temperature, the right pressure. It's like kind of like a mishmash of conditions. You got to like pinpoint exact conditions that will do this. Is it possible? And the answer is yes, it's possible. And so what we see is we deposited something on one surface and we etched it on another surface. Okay. So here is WF6 and silane. It allows for tungsten deposition. So here is the mass loading deposition on a surface. And we use WF6 and silane. And if you look at this now, it turns out that if you expose TiO2 to WF6, reaction thermodynamics, this is results from what we call HSC calculation, or HSC estimation. It says that if you take these two reactants, WF6 and TiO2, and you heat them up to 250 degrees, these two chemicals will react to produce WF2O2, which is a gas, and it will produce TiF4, which is a gas. So what it says is that all you got to do is take TiO2, expose it to WF6, heat it up, and it should etch. And you know what? Here it is. Here's the data. It etches. If you do this same calculation and say with aluminum oxide, it says it doesn't etch. And look at that, it doesn't etch. So what that means is that if I have TiO2 present and tungsten present, and you do this process, the tungsten will grow and the TiO2 will etch. This is the two same reactants, two different reactions, an etch reaction on one surface, deposition on another. So here's some, this is the thermodynamic data. So this shows that this is energetically favorable for deposition and etching. And these are the details. This is published in ACS Nano. And we can see that there's a whole other set of materials that also fit this criteria. And this kind of shows, if you start with TiO2 here, what I'm going to do is as I deposit over the tungsten, I'm going to etch, and I keep going, and I deposit more, and I etch more. So I can deposit and etch. So this is kind of, you know, this is not the same as what is going on in silicon, but it's kind of related. It's kind of related. And you can see here some pictures of the TiO2 and the tungsten, and you can see there's no tungsten on top. But notice I don't show those top-down SEMs, right? So at this time, we weren't doing that top-down SEM analysis. And that top-down, that's really what we got to do. You got to do the top-down and look, because you can just do cross sections, and it's really easy to say, oh yeah, this is perfect. But then when you look top-down, oh, there's dots. So when you see someone publishing data cross section, oh, this is perfect, you should alarm should go off. Anyway, another thing we've done. How much time do I have here? I got another couple minutes. We're also interested in how when selective deposition grows, how does the growth evolve? So what we did, this is my student Nick Carroll. We published this work. This is a simple model. We have a surface a gray area where film will tend to grow, and a light gray area where film will not grow. And remember I told you that you need some reactive sites to get the growth to start. So these little red dots, those are our reactive sites. So now we're going to do ALD. We're going to do one exposure. So the reactant is going to react with those reactive sites. Oh, this is all outlined on a two-dimensional grid. Okay, so I'm going to bring in, oh, there's my reactant. See that? Watch, I'm going to do it again. Boop, it just reacted. And what I have here is this is trimethyl aluminum. So that blue thing is aluminum, and the green are the two methyls that are left over. And those things, those attach to the oxygen, but where the aluminum is and where the methyl is, that's random. Okay, so this shows one example. If I did this example again in the computer, they would be somewhere else. Okay, so this is one example of how this might proceed. So now what happens is I'm going to bring in water, and the water is going to change these green things, these methyl groups, is going to change those into reactive oxygen. So there, I just did it again. So I just changed the methyls into OHs. So now I've got 4 OHs on the surface, and now those 4 OHs can now react with 4 more aluminum, trimethyl aluminum. Oh, there they are. And now again, the ligands are randomly arranged. And so we do that over and over and over again, and you can see that it kind of, boom, it kind of grows up and grows out and grows laterally, grows sideways. And we can do this over and over again, and what we get is we get a movie like this. So now here's my growth surface. You can see a lot of red dots on that surface. Okay, so this is going to grow here, it's not going to grow here, and this is a cross section. So here I'm going to run the movie. So there's the reaction. It's growing up and it's growing out. Okay, so we can see that it's growing. Well, that's nice. You make like a dome shape. And it turns out that because of the growth is uniform in all directions, that's what ALD is. ALD is uniform in all directions. Then you get a hemisphere. But you know what? The problem is, if you look in the literature, when you see this kind of growth, it's not a hemisphere. So it looks differently. Sometimes it looks spread out, and sometimes it's rounded. Okay? So what we did is we figured out, could we put in some sort of description for how these materials interact when they get in nearer the growth surface? So we said, oh, we could put in some sort of repulsive effects or some sort of attractive effects. And I won't go into the details of that, but you can see here, when we do that, we get a different profile. And now what we can do is we can go into literature, and we see a profile that looks like this. And this is work from Andy Kummel's group at UC San Diego. And he sees a rounded structure. And he has an explanation for why he gets that rounded structure. And it's because of he says it's because of the polarity of the water molecules. So when we restrict the polarity of the water molecules to arrange in a certain way, remember I told you the things can sit randomly on the surface. And we said, well, you know what? Let's make it so the water does not sit randomly. Let's make it so the water has to stand up on the surface. And when we do that, that's when we get that rounded shape. And so this is helping us understand the processes that are going into how these species evolve over time. And we can do things like we can look at trenches, growth up in trenches. It can look like, experiments. The other thing we can do is we can now model things that you can't physically make. So this is a structure that's only 5 nanometers. This is impossible to make physically. But in the future, people might make it. And if we do ASD on this, what would happen? What's going to happen is it's going to grow up. This is the side view and a top view. It's going to grow up and it's going to grow out. And we can predict, notice that this edge is not flat. You expect with ALD that, it's uniform growth. So you should get the uniform, nice straight line, but it's not because it is stochastic. And we can see that when you get to these atomic scale precision, this stochasticity in atomic layer deposition and area selective deposition is going to become important. So that's it. I showed you stuff that we did with, we're doing area selective deposition and how it fits into atomic scale precision in the future. And I want to thank you for your attention and take any questions. By the way, the work that I showed you was done by Hyunwoo, Juan, Hannah, Nick, Landon, Jeremy, Joe. All my groups contributed to this. So thank you for your attention.
Thanks, Greg. Now we'll have some time for questions. Dr. Ifa. Those AFMIR images were from Corey, by the way.
Don't go back to those. Thanks, Greg. What do you think is the driving force to your defects, your 93% selectivity? What do you think is getting down into those trenches?
Water is a perfect reactant for ALD. And it is a perfect, it's the perfect problem for area selective deposition. So the best ALD processes use water. And so the perfect ALD process is a lousy ASD process. So we need new ALD processes that don't use water.
Could you take your same plan, throw it into Micron's fab that's obscenely water not existing anywhere, and you think it'll improve the selectivity?
Oh, there's water. There's water in Micron's fab. I can tell you that for sure. There's water everywhere.
Yeah. But do you think it could improve comparatively to, say, a small scale lab, just simply off of the design?
Today,
no.
They agreed with me.
Okay.
The water's a problem. And that's what we're doing. We have, I didn't show it here, but we have processes where we avoid water and things get much better. But we can't do that for everything. We can't avoid water. I mean, and also there's going to be some water no matter what.
There's no further questions. I'll start calling on people. Dr. Hurley.
Okay, awesome. Yeah, thanks for the talk. How much or how important is thermodynamic modeling for the
I'll tell you what,
chemistry selection?
My student, when we started doing this etching reaction, my student said, "Oh, this is etching." This is Paul Lemaire, who now works at Lam. He said, we're doing etching. And I was like, we're not doing etching. There's something wrong with your data. There's something wrong with the mass spec. He was showing me that the mass spec, or with the quartz crystal was going down. I said, there's no way we're etching. I said, it can't be. It doesn't make any sense. And he said, well, look at this. And he went and did this thermodynamic calculation. He said, this predicts that when you put these two, this data was his data. He showed me when you expose WF6 to TiO2, you should make these two products at this temperature. And that's what's happening. I was like, okay. So how important is it? It's critical. It really teaches us what is going on. It's quite simple. This is not any kind of special, quantum calculation or anything. This is basically it's a commercially available package where it's published data. It's a lookup table, basically. You have to pay $1,500 a year. That's it.
I do. We used to have access to HSC chemistry. We still do. Okay. And version 5. Yeah, I didn't know if that was kind of always.
We have 10.
The first thing you do at the start of a ALD project.
Ours goes to 11. Yeah. So I learned from that. So now so the other thing, so now we have another program. We're studying atomic layer etching. And so we're looking at, okay, what about this reactant? What about this reactant? What about this reactant? And we put it into HSC and it says this should etch, this should not etch. And sometimes we find that HSC chemistry is wrong. And usually when it's wrong, it's because someone hasn't done an experiment. Okay? It's like the HSC doesn't know, like we think that we're making moly MON2, MONF3. Okay. We think that that's a volatile, it's like we think that that's a volatile product. Okay. But that chemical is not in HSC chemistry because no one has ever done an experiment with it. So it says that molecule doesn't exist, but in fact, we think it exists. So sometimes it's wrong, we think.
Dr. Mull.
Thanks. Cool stuff. So what I get asked usually when I teach semiconductors is silicon ever going to go away?
Well, if you look at that CFET, they're predicting it's going to turn into tungsten diselenide for those channels. So what does that mean?
But still
That
on a
means
silicon
end
wafer.
devices will be something else, but somewhere there's going to be silicon. Silicon is never going to go away. I mean,
Oh, do you
never say
really want
never.
to say that?
my mother
Never?
told me- my mother said, never say never. So, but in my lifetime, I can tell you my lifetime. And I can say that because I'm pretty old, so I'm not going to live for much longer. I mean, I'm going to live much longer, but I'm just saying that I'm never going to see it go away. How about that? It's never.
You know, the chairman of IBM once said they thought there was only need for 3 computers in the world. Way back, like in the,
They said there's only going to be 3 computers
there's only need for
Only
3
need for
computers
3
in the
computers.
world. Way back, like in the early
until they
70s.
realized they could make a small one and sell it to people. By the way, I used to work at IBM, and I worked on displays. This is in 1992. And we were making a display about this big, and we were trying to decide, should we try to make a bigger display, or should we try to make a higher, you take this display and make the same pixel, but make it higher resolution. And we're saying, who's ever going to want a little screen? People aren't going to want little screens. And there was a research group that was like taking a little screen and making like a little tiny computer with a little tiny keyboard. It looks like a little mini PC, right? A little tiny keyboard. And we were laughing. It's like, who in the world is ever going to want a little tiny keyboard with a little tiny display? No one's ever going to want that. We were experts, flat out wrong. Flat out way wrong.
Hi. What are some of the bottlenecks when approaching these devices that are just a few atoms thick?
What are the bottlenecks I see? What?
Like some of the troubleshooting you find when you're approaching these devices that are only a few atoms thick.
Yeah. So what are some of the bottlenecks? Some of the bottlenecks are impurities. So you have to avoid any kind of impurity. Just also statistics. It's like if you think about the impact of one defect, how one defect could lead to more and more defects. So the other thing I think about is I talk to people, like this, and I'm working on selectivity, and people say, oh, I'm working on selectivity. I'm interested in selectivity in biology, right? So we know that enzymes bind selectively to some substrates, right? So what is the selectivity of biological processes? How do you quantify that compared to the selectivity we need here? And I've been trying to get my head around how do we do this. My gut feeling is the selectivity that we need, this selectivity we need is like many, 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 many orders of magnitude more demanding than nature's selectivity in biology. And so we've survived and we've, evolved because of chemical selectivity in our biological systems. But the chemical selectivity that's driven our evolution is kind of crude compared to what we need for this. So when I think about the demands of what are we really controlling? It's a huge bottleneck to understand that. Is that it? I was telling somebody, I gave a talk like this at Samsung, 45 minutes, and they grilled me for 45 minutes. So you got a ways to go.
Well, I can ask a question. You're showing your model with Nick here, and you see the mushrooming, right? So the mushrooming is a big problem. So does your model provide you insights to shut down the mushrooming behavior?
Yeah, so what we can do, what it tells us is we need to make bigger, taller passivation layers. So if you make a bigger passivation layer, then it's kind of obvious, right? If you can grow from the bottom up, that's how you do it. And actually, Stacy showed some results last week, a couple weeks ago. It's at AVS, where she made a big, thick passivation layer, and she got it to grow up. And she showed her passivation layer was this thick, and she got it to grow up, and it continued to grow up and didn't go over the passivation layer. I said, "What's up with that?" She says, "I don't know." So we don't know what's going on in many of these cases.
Yeah, I mean, my same question for her was, if you really want to have the lack of mushrooming, are you going to need one of these basically like double area selective processes where your passivation layer was selective, like a selective deposition process that somehow just magically didn't mushroom?
Yeah, so what we wanted, I told you we were working on combining selective deposition. What we wanted to do is we wanted to do them side by side. So we could do one, then another, then go back and do one, do another, go back and do one, and build up straight up without, build straight up from the bottom. That's what we wanted to do. And we haven't been able to do that yet.
It's almost like we need a database of area selective processing.
Yeah, and we were working on that too, as you know.
All right, well, let's thank Dr. Parsons for a great seminar.
Thank you all for your attention. I appreciate it.